Hello, welcome to lecture 20 of Elec Eng2CI5. In this lecture, we'll discuss the solution of first order circuits. We call it here systems, but it's really circuits. And these are circuits that include only one energy storing element. So it includes only one inductor or one capacitor. And when you try to write KCL and KVL for these circuits, you will end up by first order differential equation. So we'll see how we can solve these equations using the initial value problem. And the approach we adopt in this video is really a mathematical approach. In the following video, we'll be discussing more a circuit theoretic approach, how to use Thevenin theorem in order to calculate the different voltage and current waveforms. So as I mentioned, we are discussing in this video first order circuits. These are circuits that contain only one energy storage element. Remember, the capacitor stores electric energy in its electric field, in the insulation material, and an inductor stores energy in the magnetic field. So each one of them is really an energy storage element. If you try to find, if you write KCL or KVL for some of these circuits, you will end up with a first order differential equation. The reason for that is that the current going through the capacitor is equal to C dVc by dt, and the voltage across the inductor is equal to L dIL by dt. So when you write KVL or KCL in some cases, you obtain a first order differential equation. So now our target is to find the waveform for the voltage and current everywhere by solving this first order differential equation. It has to be very clear that what we are doing right now is called transient analysis. It's not really DC. DC assumes that nothing is changing with time. While transient analysis assumes we are going through some transient behavior, you close a switch and then the capacitor takes some time until they are charged, or the inductor takes some time until its magnetic field is built. Okay, so this is not really DC anymore. It's not steady state. This is called transient analysis. We'll start by discussing first the template, and then I will show you how to apply this template to many circuits. So we are giving here a differential equation in the form dx of t by dt plus ax of t is equal to f of t. X of t can be a current or a voltage, a is a constant, and the f of t is our excitation. And we are going to limit ourselves a little bit further to the case where f of t is a constant. It's constant a. So we have small a is a coefficient. We have capital A, which is our excitation, is a constant. So this can be a constant current source or a constant voltage source, an independent current source, independent voltage source. A DC, I mean by constant I mean is DC, does not change with time. So the initial trial or the initial approach will apply to a system of this form. Dx of t by dt plus ax of t is equal to A. Remember, x of t can be voltage or current, A is a constant, and capital A is a constant. This system, from our study from mathematics, we know that it has two solutions, a homogeneous solution and a particular integral solution. A homogeneous solution is the solution we have when we set this A equal to 0, when there is no excitation. It's a solution or response due to the initial conditions on the energies in the energy storage elements, in the capacitors and the inductors. The second one, particular integral, is the one due to the excitation itself. From our study of mathematics, we know if you have a system dx of t by dt plus ax of t is equal to 0, this is a homogeneous system, then the homogeneous solution is given by x naught e to the minus at. X naught is some initial value that you determine through the initial voltage or initial current in your circuit. Notice that x naught is a constant, does not have necessarily to represent the value of the voltage and the current at the beginning. But what you have to do, you have to say at time 0, when you put t equal to 0, this term becomes 1, then x of 0 will be equal to x naught. Okay, in some applications you have another constant you have to take into account. I will show you this later. But this is a solution, this is what we call the homogeneous solution. This is a homogeneous solution when you put your excitation equal to 0. The capital A here was set equal to 0. Okay, so this is a homogeneous solution. It's a decaying exponential where E, of course, I hope you understand. You know this. This is called the Euler constant. 2.718, and this is the expression for this solution. The second solution we have is called the particular integral solution, XPI. And the XPI is due to the excitation. And when you have a differential equation like this one, and you ignore the initial conditions, so zero initial conditions, the solution that you can get from this one is equal to A capital over A small. Okay, so this is a particular integral solution. So we now found that the homogeneous solution is x naught e to the minus at, a small multiplying t. We have found the particular integral solution, which is a solution due to the excitation only. It's equal to its constant a capital divided by the constant a small. Okay, so now we have the complete solution. The complete solution is the homogeneous solution plus the particular integral solution. So we sum these two solutions and then we obtain our complete solution for the voltage or the current. So what's going to happen right now, we're going to start by solving circuits. We'll apply KVL and KCL, try to find the first order differential equation governing these circuits, and then using this template, we try to write the expression for the voltage and current and apply any initial condition that we need to apply. One word of warning I need to remind you of: when we talked about the homogeneous solution and we said that the X homogeneous is equal to X naught e to the minus at, this formula allows you to apply boundary condition only at time t equal to 0. In other words, you can't apply boundary condition at time t equal to infinity because this term will be 0. You can't apply boundary condition at time t equal to minus infinity because this term will be infinity, which is not physical. Okay, so this expression assumes that you can put the time, you can put boundary condition or initial condition. You can call it, I call it boundary, but it's the initial condition at time t equal to 0. Okay, this is very important later when we start to discuss multiple solutions with multiple stages, as I would show you later. Let's have our first example. We have a capacitor that initially had a voltage of 5 volts, so it was charged somehow. This switch was opened, so it's not connected to the resistor. And then the switch was closed at time 0, so the capacitor will start to discharge. We know actually before we do the solution what's going to happen. When you close this switch, because this has 5 volts, then a current will start to flow in the circuit, and then the charge in the capacitor will start to decay gradually and slowly. The voltage in the capacitor will also decay gradually and slowly until you reach a steady state where everything is 0. Okay, so the energy that was stored in the capacitor dissipated in the form of the power delivered to the resistor, which dissipates in the form of heat. Okay, so let's now try to find this mathematically. So what we're going to say, we're going to write the only equation we can write here, that the voltage across the capacitor is equal to the voltage across the resistor. And the voltage across the resistor is the current going through the circuit multiplied by the value of the resistance. Okay, so we apply this equation and then we try to formulate it in the form of a first order differential equation. Okay, so the capacitor, the switch is now closed. The capacitor has initially 5 volts. Okay, so one word of warning: the capacitor current is always flowing from positive terminal to the negative terminal. So if it is considered to be a positive current, this is its reference direction. So this is the reference direction. So the equation that I have here applying KVL is that VC, which is this voltage, is gonna be equal to VR, which is this voltage here. This is VR with this polarity. So VC is equal to VR. But what is VR? VR is equal to the current IR multiplying R, which is 1 kilo ohm. But this IR is equal to minus IC. It's very important to notice that, because this is the reference direction of the capacitor current. It's assumed to be positive from positive terminal to negative terminal of the capacitor. So this current IR, which is flowing this way, is negative IC. So we can simply write it this way, that VC is equal to VR, which is IR multiplying R, but IR is minus IC. And also now we're going to replace the capacitor current by C dVC by dt. So now what we wrote, this is the equation we're looking for, that VC is equal to minus RC dVC by dt. Let's move this one to the other side and let's divide both sides by RC. We obtain this expression. This looks pretty much like the template we have. dx by dt plus a multiplying x of t is equal to 0. Here the capital A is equal to 0, but the small a is 1 over RC. Okay, so what we did, applied KVL, we obtained this first order differential equation. This looks like dx by dt plus a small a multiplying x of t is equal to 0. So a is equal to 1 over RC, and I know that the solution of this problem now is VC of t is equal to a constant multiplying e to the minus t over RC. E to the minus AT. This is e to the minus AT, but a is 1 over RC. Okay, and this is what we call V naught e to the minus t over tau. I called this term RC to be equal to tau. Now, it's very important to understand that if you multiply a resistor with a capacitance, you get a quantity that has units of time, and we call this the time constant. This determines how fast the capacitor is going to be discharging. If the resistance is too small, then the capacitor will supply higher current, because remember the current flowing here is equal to Vc divided by R, and then the capacitor will be drained faster, and tau will be a small number. Okay, but if the resistance is big, this means that the current drawn from the capacitor will be weak, and then the capacitor takes long time to discharge, and the RC will be relatively larger. Okay, so we wrote Kirchhoff KVL. We wrote it in the form, the template we derived earlier. We found that A is 1 over RC. Then our solution is V naught e to the minus AT, but A is 1 over RC, and we call the RC tau. What is the value of V naught? Here, because we have the voltage at time 0, was equal to 5 volts. We're told at the beginning that the voltage here before the switch was closed was 5 volts. Then if you put t equal to 0, this term becomes 1. And then you know that the constant V naught must be equal to Vc of 0. Okay. So let's calculate tau. The resistance value is 1 kilo ohm. The capacitance is 1 microfarad. You multiply these two together to get 10 to the minus 3 seconds, so 1 milliseconds. So the capacitance, the value of the voltage across the capacitor is 5 e to the minus t over tau. T over tau means t over 10 to the minus 3, so it becomes e to the minus 1000 t. What does tau signify? Does it signify? Tau is a very important parameter. We use it to characterize the charging or discharging of capacitors and inductors. So here the capacitor at the beginning had 5 volts, and then start to discharge according to the relationship 5 e to the minus t over tau, where tau is 10 to the minus 3. So this becomes e to the minus 1000 t. So this means that after time tau, let me maybe write it here on the side. So I can simply write it this way: Vc of t is equal to 5 e to the minus t over tau, correct? And tau is 10 to the minus 3. If t is equal to tau, so if I select here this t, the time t, to be equal to tau, this gives me e to the minus 1. So I can simply write that Vc at time tau is equal to 5 over e. It's 5e minus 1, which is 5 over e, which means that the voltage across the capacitor dropped from 5 to 5 over e, which is equivalent to multiplying 5 by the constant 0.368. So 0.368 is 1 over e, so 1 over 2.718. Now, if you allow the capacitor, if you follow the capacitor voltage for one more tau, so t here becomes 2 tau. If this becomes 2 tau, then 2 tau divided by tau, you get e to the minus 2, which is e squared, 1 over e squared. So you can simply say that Vc at time 2 tau, if you substitute here in this exponential, put t equal to 2 tau, you get e to the minus 2. So this will give you 5 over e squared. 5 over e squared is equivalent to multiplying 5 by the constant 0.13. So tau determines how fast the capacitor is discharging. After 1 tau, it goes approximately to about 1/3 of its initial voltage. After time 2 tau, it goes approximately to maybe 1/7 of its initial value, and so on. So tau can be smaller by making R smaller or making C smaller, and tau can be larger by making R bigger or making C bigger. Okay, so we can by reducing R and C, we can make tau smaller. By increasing R and C, we can make tau bigger. Okay, so tau is our time constant, and it's whenever in this course we refer to time constant when you have a capacitor, we mean really RC, the product RC. So this gives the expression for the voltage. What about the current? What about the current in the circuit? I'm not showing that here, but I think it's very important to mention it. We have a capacitor, okay, and this capacitor is discharging through the resistor, okay. This is VC here, so this voltage VC, and this is R. The current going through the circuit from KVL, if I'm gonna call this one I, this is IR, okay. This IR, this current here, is nothing but VC divided by R. So it's gonna be following exactly this waveform. So this starts by 5, because R is 1 kilo ohm. 5 over 1 kilo ohm will give you 5 milliampere. So it's 5 milliampere, and then starts to go down gradually and slowly in the same curve. So the current waveform will start with 5 and then goes 5 milliampere and then start to go down slowly up to 0. Okay, it's very important to understand that for this case, both the current and voltage are decreasing with time. Okay, let's consider one more example. Here we have a capacitor that has initially 0 voltage. The capacitor is this switch is opened, then there is no voltage anywhere, and then at time 0 you close the switch. We know what's going to happen from our discussion in class. The battery will start to supply current, and this current will start to accumulate positive charge on this plate, negative charge on this plate. The voltage across the capacitor will start to build up until time infinity, until steady state has been reached. The capacitor voltage will be exactly equal to 10 volts, and the capacitor will look in this case like open circuit. Okay, so we know beforehand what will be VC of infinity. I know what's be VC of infinity, and I know also at DC, when we reach steady state at infinity, when this is 10 volts and this is 10 volts, there will be no current in the circuit because the capacitor represents effectively open circuit. So I know before I do any solution that VC of infinity is equal to 10 volts, the capacitor is fully charged, and then the capacitor is fully charged, dVC by dt will be equal to 0, which means IC will be equal to 0, which means that this open circuit and then there is no current in the circuit. We are gonna show that we can write the differential equation governing this circuit, and then we use the template that we derived earlier to get the expression for the voltage and the current. Okay, so at time 0 we know that the switch was opened before time 0, so this was opened, the battery is disconnected from the circuit, this one has 0 volts, then we know that everything is stable. Okay, now you close the switch, immediately after you close the switch, and I'm gonna correct myself here, I'm gonna write it as VC of 0, I'm gonna write it as VC of 0 plus. VC of 0 plus, I mean by it the value of the capacitor voltage immediately after I close the switch. It must also be 0. Why? Because as I explained in class, the capacitor voltage cannot change instantaneously. It was 0 at VC of 0 minus, just before you close the switch. Immediately after you close the switch, it will still be 0. Okay, but the circuit now is conducting current, and the current is flowing will be equal to the 10 volts divided by 10K. So immediately after you close the switch, the capacitor cannot change instantaneously. The voltage across it will be 0. So VC of 0 plus will be equal to 0 volts. And what I'm gonna write this one as well as VC of 0, IC of 0 plus. Okay, and this one here, immediately after you close the switch, the current flowing in the circuit, which is I of t, and this is exactly the same as IC of t, because we agreed that the capacitor current is always flowing from the positive terminal to the negative terminal. So I of t is equal to IC of t, and this will be equal initially to 10 volts divided by 10K. Remember, there is zero drop here. Okay, so this is 10 volts divided by 10K. This is gonna give me 1 milliampere. This is simply by applying KVL here. This is 0 volts, this is 10 volts, and this one is IR. Then I is equal to 10 volts divided by 10K, so it's gonna be equal to 1 milliampere. Now let's apply the governing equation. I need some initial conditions. And as I explained from that template, you need the initial conditions at time 0. So now let's apply KVL. What does KVL say? That this voltage here would be equal to this drop plus the voltage across the capacitor. So I'm gonna write this one here. This is positive, negative. This is the voltage across the resistor, and this one here is the voltage across the capacitor. This one here is equal to IC multiplying R. Remember, this is I, which is the same as IC. So this drop is IC multiplying R, and this one here is VC. So 10 volts is equal to IC multiplying R plus VC. And I'm going to replace IC, which is I, by C dVC by dt, because the current flowing in the circuit is the derivative of the capacitor voltage. Of course, with this constant of proportionality, which is R. Okay, this is simply from the equations governing the capacitor. This looks like the differential equation we discussed earlier, but I need to make the coefficient of dVC by dt to be equal to 1. So I'm going to divide both sides here by RC. If you divide both sides by RC, you get this expression, dVC by dt plus 1 over RC VC of t is equal to 10 over RC. Now, this is the same template we had earlier, because the template we had was dx by dt plus small a multiplying x of t is equal to capital A, which is another constant. Then our general solution is that the capacitor voltage is equal to some constant e to the minus at. A here is 1 over RC plus this constant capital A divided by the small constant a. If you divide this one by this one, you get 10. Okay, this from the template we started with. So this is now the expression for the capacitor voltage at any time t. And of course, this and I'm warning you again that this template assumes that you start at time 0, so you have to put initial conditions, or we call it boundary conditions, at time 0. So at time 0, if you put t equal to 0, the voltage was equal to 0. So this term at time 0 will be equal to 1. Then you get V naught plus 10 is equal to 0, because at 0 we had 0. So 0 is equal to V naught plus 10, then V naught is equal to minus 10. So if you organize everything together, this is minus 10 e to the minus t over RC, and RC, I'm going to call it again tau. It is the time constant of the circuit. It determines how fast the capacitor is charging or discharging. Okay, so minus 10 e to the minus t over tau plus 10. Okay, I take 10 out as a common term, I end up with this one here. So now this is the expression of a capacitor that's charging. Why? Because at time 0, if you put t equal to 0, this becomes 1, you get 1 minus 1, then VC at time 0 is 0, which is fine because we started with 0 initial values. At time goes to infinity, if this goes to infinity, then if t goes to infinity, then this whole term will approach 0. And then you get 10. So the capacitor voltage really looks something like this. It starts with 0 at time 0, and then it goes up to 10 at infinity. Okay, so it's the expression of a capacitor charging. Okay, this is VC of t. The speed at which is, or the rate at which is charging is determined by tau. Tau is RC. R is given is 10 kilo ohm, and C is 5 microfarad. You multiply these two together, you get 5 multiplied by 10 to the minus 2, which is 50 milliseconds. Remember, RC will give you units of seconds. So this is 50 milliseconds. But we multiply by 1 over tau. So 1 over 50 milliseconds will give us 1000 over 50 will give us 20. So 1 over tau is equal to 20. So this term here is really e to the minus 20t. So the expression for the voltage is VC of t is equal to 10 multiplying 1 minus e to the minus 20t. It starts at 0 and then it approaches 10 at infinity. What about the current? the current, we can calculate the expression for the current, because the current in the circuit is the same as the current flowing in the capacitor, is C dVc by dt. So you take this term and differentiate it relative to t. The derivative of minus 20 e to the minus 20t will give you minus 20 multiplied by e to the minus 20t. So you get 10 multiplying 20 multiplying e to the minus 20t, and minus sign will cancel with minus sign. Okay? And this whole thing will be multiplying the value of the capacitance. So this is here, the capacitance value is 5 microfarad. So this 5 microfarad, and the derivative of 10 e to the minus 20t, actually it's actually minus 10 e to the minus 20t, you still have the minus 10, the derivative of e to the minus 20t is minus 20 e to the minus 20t, and this is C. If you collect all these coefficients, this will become positive. This will give us 200 multiplied 5 to the minus 6. Okay, so this will give us 10 to the minus 3 e to the minus 20t, which is correct, because we knew I mentioned in the beginning that the current at time 0 was equal to 1 milliampere. So you start with very strong current at the beginning, and then because the capacitor is getting charged more and more and more, there will be less current in the circuit until it's fully charged. Then the rate of change, the slope of the voltage is equal to 0. There will be no current in the circuit anymore. Okay, so at steady state, 0 current, 10 volts across the capacitor, and the capacitor looks like open circuit. This is a little bit different from the previous example. Previous example, both the capacitor voltage and current were both decaying with time, while here you have the capacitor voltage is increasing with time, while the capacitor current is decreasing with time. Okay, let's consider one more example. We have here an example of a circuit that was under steady state before. So this switch was closed from minus infinity up to time 0. Okay, and then at time 0 suddenly it was opened. Okay, so what we can tell just by looking at it was what was happening. When you close the switch in the beginning at time minus infinity, this battery will start to supply current and will start to charge the capacitor. Steady state will be reached only if the capacitor voltage will be equal to 24 volts. Why? Because if this was less than 24 volts, then if you apply KVL, you will have a current, you will have a drop across this one. But if there is a drop across this one, this means there is still a current going through. But if there is a current going through, this means that the capacitor is still charging, a contradiction. So the steady state is reached when this is 24, this is 24 volts, there is 0 drop here, means there is no current flowing here. Okay, so the capacitor looks like open circuit. Now when you open the switch, the capacitor is fully charged to 24 volts. Now the capacitor will start to discharge in these two resistors. Now this is disconnected, the battery is not there anymore. It will start to discharge in these two, R1 plus R2. R1 is 1 ohm, R2 is equal to 2 ohm. The capacitance value as given, 0.167 farad. So from minus infinity to 0, this switch was closed. The capacitor reaches steady state, it's 24 volts. So I know that just before the capacitor was opened, Vc of 0 minus, this is what this means. Just before the capacitor was opened, the capacitor voltage was 24 volts. Just before after the capacitor was opened, it will also still be 24 volts. Why? Because the capacitor voltage is continuous. It cannot change its value instantaneously. Okay? Now we can use that to do our second part and calculate the discharge profile or discharge waveform of the capacitor voltage through these two resistors. So this is the first situation we have. I'm showing the situation from minus infinity to 0. The switch has been closed. The battery supplied lots of current until we reach a steady state, DC. Well, when would that happen? This must be equal to 24 volts. Why? Because if it's not 24 volts, say if it's only 12, then there is another 12 here. And if there is another 12 here, this means there is a current going through, which means that the capacitor is still charging, a contradiction. So if the capacitor to be fully charged, this must be 24 volts. So between here and here, you're going to see still 24 volts. Okay, which means between here and here, you're going to see 0 volts. And in that case, there is no current flowing here. The current must be equal to 0, and the capacitor represents open circuit. So this is a steady state. Okay, so we know now, just before we open the switch is here. This is, I'm not showing the switch. The switch S is really in this part. This is S here. Okay, it's closed now. At time 0 it was opened. Okay, so when you open the switch, it was opened. Okay, and then the capacitor will start to discharge in these two resistors, the 2 ohm and the 1 ohm. Notice again, as I said, once you open the switch, the capacitor voltage does not change instantaneously, neither the inductor current. So they're going to maintain the same value before and after any change in switches. So VC of 0 plus after you open the switch, just after you open the switch, is equal to VC of 0 minus just before you open the switch is equal to 24 volts. This will give us the initial value we're going to be using for the second stage when this switch was opened from its position. Now the switch has been opened, so I'm not showing that part anymore, but it is there. So you have this switch opened and the battery is there. They don't really contribute anything because the switch is disconnected the battery from the circuit. So what do we have now? We have a capacitor that initially had 24 volts across it, and it now will start to discharge like the first example we had in this video through the 3 ohm resistor. Remember this 3 ohm. So I don't have now to reinvent the wheel again. You can write the expression of the discharge in the very similar to the first example we had, but I know it's going to be a discharging curve from 24. So it's going to be 24 e to the minus t over tau, and tau is C multiplying by R equivalent, the total resistance seen by the capacitor. Okay, if you go back and write the expression, you will see here that you have 2 ohm plus 1 ohm in series. Then the total resistance seen by the capacitor is 3 ohm. So this is why tau, which is the time constant, is equal to R equivalent multiplying C is equal to 3C, and C is 0.167, and the numbers here are selected to give you 0.5 when you multiply these two together. Then our time constant is 0.5 seconds. So this circuit takes longer time to charge and discharge because the capacitor value is very high. It's not really microfarad anymore. It's 0.167 farad. So it takes long time. So the expression for the capacitor voltage, and here I'm using the same knowledge I learned from the first example, is going to be VC of 0 e to the minus t over tau. VC of 0 is 24. We start with 24. And if you put 1 over tau, 1 over 0.5 will give you 2. This e to the minus 2t. What about the current? The current, as we agreed, if you have a capacitor discharging, the current will also be decreasing with time. So the capacitor, I can try maybe to draw for you the value of the waveform for the capacitor voltage. So it's becoming a little bit faint here. So it goes down like this. Okay, you can go back to the backlight again. So it goes down like this here, and it starts from a value of 24, and then it goes down to 0 gradually with time. The current will be exactly the same. In the beginning, you have a current. What is the value of the current at the beginning? Well, we had 24 volts across this one in the beginning at time 0, and you have 3 ohm. Then the current will be in the beginning 24 divided by 3 is going to be 8 ampere. So it starts with 8 ampere and gradually and slowly starts to decay in the same way. So it follows this profile exactly, 24, and then it goes down by the same rate here. So I'm sorry, it's not 24, it's 8. So it's going to be 8 e to the minus 2t. This will be the value of the current. So the voltage is 24 e to the minus 2t, and the current will be 8 e to the minus 2t. Okay, we now move to the last example of this video. We're now talking about an inductor. Again, we have two situations here. This capacitor, or this switch, this switch here was kept at this position for a very long time. And then suddenly at time 0 we moved it to this position. So what's going to happen, this current will cause the inductor to start to build up its magnetic field. So it will build up its current. So the inductor will build the current, okay, and there will be energy stored in its magnetic field. Steady state is reached when the inductor magnetic field is fully established, okay, and in that case the inductor will represent short circuit. But if you draw this circuit here as a short circuit, you will see that this 12 milliampere will have to go through the inductor alone. Nothing is going through this one here. So in steady state, before the switch was moved to the other position, this 12 milliampere will have to fully flow in the inductor, and the inductor will represent short circuit. Okay? The energy is stored in its magnetic field, and the inductor current is equal to milliampere. Now, when you move the switch from here to here, the current of the inductor cannot change its direction or value instantaneously. So we can simply say that IL at 0 minus is equal to IL at 0 plus is equal to 12 milliampere. The current will still be flowing this way. Okay, but now it's gonna flow through the resistor. Okay, so in the beginning it will be 12 milliampere as well. Let's see how we can write the differential equation for each stage, and how we need to write it in the form that we developed in the beginning of this video, and let's see how we can use this one to determine the value of the current. So this is the first situation we have. The switch is closed in position number 1. The rest of the circuit is disconnected. So there was some transient behavior that happened at minus infinity, but now we are talking about from minus infinity to 0. Okay, and I am giving you a warning here. In the first stage, the switch was in its position from minus infinity to 0. But when I'm gonna use my calculations, because the template we're using assumes 0 at the beginning, minus infinity here will be my 0 really. Okay? But when I move to the second stage, I will have to use the final value I reach here as the initial value for the second switch position. Let's see how this is gonna work. Let's consider this circuit alone. Let's consider this circuit alone. We need to write the differential equation governing this circuit. So you write it through writing KCL. 12 milliampere is equal to this current plus this current. Okay? This current here, the current flowing here, okay, is equal to the inductor voltage VL divided by R. Okay, this is the inductor voltage. This is the inductor voltage here, VL. If you divide it by this R, you get this current. What about this current? This is the inductor current, which is equal to, we can of course, we'll keep the inductor current as it is, but what we're going to be doing, we're going to replace the inductor voltage as L di by dt. So after you wrote this current here as VL over 6 kilo ohm over R, I'm going to replace this VL by L di L by dt, because I need to keep everything in terms of the inductor current. So for capacitor circuits, we keep everything in terms of the capacitor voltage. For inductor circuits, we keep everything in terms of the inductor currents. So this is, I simply applied KCL here. Current flowing in equal to sum of two currents flowing out. This one is IL, this one is VL over R, and VL is nothing but L di by dt. Let's organize it. Let's make the coefficient of DIL by dt to be equal to 1. So this is the expression that I have. This expression is the same one we started the video with, because it looks like dx of t by dt plus a small multiplying x of t plus capital A is equal to 0. Is equal to capital A, or minus A minus capital E is equal to 0. So dx by dt plus a small x of t is equal to capital A. So I know all these coefficients, I know them, I know what's R, I know what's L, I know now what's small a, I know what's capital A. I can write the solution for this first stage. Okay, so let's see how we can do that. So I replaced all the coefficients by their numbers, and this is what I found out. I found that A is 6 multiplying 10 to the power 6, and capital A is 72 10 to the power 3. Please verify these numbers yourselves. This is the same template we started the video with. So my solution will be a constant multiplying e to the minus at here, okay, plus this term capital A divided small a. So you divide 72 10 to the power 3 by 6 10 to the power 6, you end up by 12 10 to the minus 3. Now we know that at the very beginning, of the switch in position number 1, that we assume here that the inductor did not have any current. Remember, even though we started really at minus infinity, but this template allows me to impose condition only at time 0. So minus infinity of position minus 1 is really 0 in this formulation. So I'm gonna here put t equal to 0. At time 0 I was having 0. Then I know that this whole thing must be equal to 0. This is gonna give me 1. Then I naught plus this term will be equal to 0. Then I naught is minus 12 milliampere. If you put everything together, very similar to the capacitor example we did, this is the expression for the inductor current in the first stage when the switch was in position 1. Okay? Of course, at steady state, as I knew beforehand, if time t goes to infinity, which you will approach our 0 for position number 2. If this goes to infinity, this becomes 12 milliamperes. So we know now when we get this value, this will be the initial value for the second stage when the switch was moved to position 2. Okay? So I now know the inductor current is equal to 12 milliampere. So what I can conclude from this one is that I can write it this way here, is that IL at 0 minus will be IL at 0 plus will be equal to 12 milliampere. So when you start the position in the inductor in position 2, switch in position number 2, you start with initial value of 12 milliampere. Now we switch the switch to position number 2. Okay, so the current flowing here in the beginning, let me erase this one. The current flowing here in the beginning, flowing here is 12 milliampere, and it cannot change its value instantaneously. I mentioned to you before, in the inductor, the inductor's current has to be continuous. So when the switch was connected on the other side, it was 12 milliampere. It cannot change. After you change the switch, it will still be 12 milliampere. But this 12 milliampere will now flow in this resistor. So what does it do? It's going to actually supply this current to the resistor, and it will start to lose its energy gradually and slowly until it's fully discharged through this resistor. Let's write the equation governing this one. The equation governing this loop is that VL is equal to VR. Okay, but this VR is equal to IR multiplying R, but IR here is minus IL. Okay, so the expression to write is that VL, which is the voltage across the inductor, is equal to the voltage across the capacitor, but the voltage across the capacitor, excuse me, voltage across the resistor, the voltage across the resistor is equal to the current, this current here multiplying R, but this current is minus IL. So this is why I had this negative sign, and I'm gonna now replace VL by L DIL by dt to write my differential equation. You make the coefficient of DIL by dt to be equal to 1 by dividing by L. You obtain this expression. This is the same expression we started with. dx of t by dt plus a multiplying x of t is equal to 0. This is a homogeneous case when capital A is equal to 0. R2 over L will give you 10 to the power 6, because this is 1 key and this 1 millihenry. So 1 key over 1 millihenry will give you 10 to the power 6. Then I know that the capacitor, the inductor current will have the profile I naught e to the minus 10 to the power 6. Okay, so it starts initially by 12 millihenry, and they gradually slowly start to die with time as it heats up the resistor. So resistor is the energy is moved to the resistor and it's being dissipated in the resistor. What is I naught here? This constant, put t equal to 0. This term here will give us 1. So I naught is the inductor current at time 0, which is equal to 12 milliampere. This is the same current we got from the previous stage. Then the last step we have is this, and this is the value of the inductor current. IL is equal to 12 milliampere e to the minus 10 to the power 60. And you see it decays very fast. In to get e minus 1, you need only 1 microsecond. 1 microsecond, and this thing here dropped to e to the minus 1. So it goes to e to the minus 1 of its time. So here the tau is just 1 microsecond. So this is how the circuit functioned. At time 0 here, you started with minus infinity, I'm sorry. This was when the switch was in position 1. The inductor's current built up from 0 up to 12 milliampere. It reached steady state. This is considered infinity. This point here is infinity of the first stage, which is 0 the second stage. Now the switch was moved to position 2. The inductor started the discharge. It went up 12 milliampere up to 0 at infinity. Okay, so this is really how the inductor current goes, and we'll be addressing more examples about this when we discuss the Thevenin, how Thevenin equivalent can be used to analyze such transient circuits.